So we finished talking about the natural extension of single variable integrals into multivariable situations, and that's the so the multiple integrals that we talked about in the previous chapter. And what I want to do in this section is talk about yet another type of integral. So just like when we had derivatives in the multivariable context, we could come up with various different ways of taking derivatives, including the gradient, the divergence, and the curl, and so on, which is also reflected in the fact that multivariable functions can be vector valued functions as well. So when we have that fact at our disposal, and the fact that you're in multiple dimensions, say 2 dimensions, 3 dimensions, and so on, it turns out that there's a much richer collection of integrals that you can do. And what we are going to be talking about here is something which is called a line integral, excuse me. So it's a new type of integral. This is also sometimes called a path integral. So integration along a path. And a path is a better word here, because when you say line, it means like it's a straight line. Well, it doesn't necessarily have to be a straight line. It can be just an integration along a curve, basically. Right? So that's what this is about. Okay, so how are we going to talk about line integrals? So let me just take a step back and give you a concept from physics, and this is going to motivate us in defining a type of line integral, right? So the physics concept is something which is called work, right? So you might have heard about this. So if you have a little object over here, and there's a force which acts on it, and you move it from this point to this point over there, right? So the force, while the force is acting on it, you move it in that direction, and this displacement vector is the vector r. If so, the work done by the force in moving this object from here to here is given by, well, it's just a product of the magnitude of the force times the magnitude of the distance that you've gone, right? So as long as you're going in the same direction, and as long as the force that you're talking about is constant. So this is a very important concept in physics, and relates to conservation of energy and so on and so forth, right? So the concept of work. We are not really going to get into physics in a broad sense, but we need to just take this as a sort of definition to help us motivate the next type of integral. Okay, but what if you take the object. Now earlier we took it from here along the same direction as the force was in that direction, but what if you take it in a different direction like this, right, to some point over here? So your displacement vector is r, and f is as well. It turns out that in that case the work done is given by f dot r, and this is the component of f in the direction of r. Right? So when you're doing this, you're taking the component of f in the direction of r, and why is that? Well, let's see, right? So one thing that I do know is that so if I call this angle here theta, right, the angle in between these two things theta, I know that I can write f the dot product as the magnitude of the first vector times the magnitude of the second vector. These are the norms, times cosine of theta, right? So I can write it in this way, and let me just take this f cosine theta. So f cosine theta is actually the component of f in this direction, in the direction of r, right? So this f here, this vector, I can decompose it as a vector in that direction plus a vector in that direction, right? It's the component in this direction, which is f cosine of theta. So this is f cosine of theta times the size of r. Okay, so this is the concept of work as long as we still have a constant force. What if the force is not a constant, right? So now let's take it to the situation where we have a force field, let's say. So this could be something like gravity, right? So if your gravity changes with depending on your location, if you're really far away from Earth, the gravity is going to be quite different from the gravity on Earth, right? So, or electric fields, magnetic fields, and so on and so forth. So suppose you've got some force, right? Let's think of this as a force, but it's just in general any old vector field which depends on space, right? And we want to look at the work done by this in moving an object along some curved path, right? So C here is some sort of curved path in space in R3, right? So now F is a vector field, so at different points on this path, f is going to be different. It'll be pointing in different directions. It might be much bigger in size, so it's quite large over there. It's pretty small over here, and so on. So f depends on your location, the direction, as well as the amplitude of it depends on direction, right? So let us think of a general point on the curve as having coordinates x, y, and z. So I can think of it as xi plus yj plus zk. And what I want to do is I want to extend this notion that we had over here of work. So in this case, as long as F and R were both constants, the work done was just F dotted with R, right? So in this case, things are a little bit more complicated because F is changing depending on where you are, and you're going along this curve. You're not going along a straight line either. So there's some sort of difficulty. Can we still figure out what the work done is? Well, it turns out, right? So let's just take one location. Let's suppose that's a general location R. And let's suppose we go to a location R plus, well, I'm going to write this as R plus dr. Think of this as R plus delta R, where delta R is some really small quantity. So this continues to remain on the curve C, right? It continues to remain on that. But I'm thinking, rather than writing delta R, I'm bravely writing dr, which is a differential element, indicating that I'm thinking of this delta R as being incredibly small. So I have my location R, and I'm going to another location which is very close by. And the point is that while I'm doing this, because I'm thinking of this as incredibly small, I may as well think of F as being constant for the duration of that tiny motion. And if it's constant for the duration of that tiny moment, the amount of work done during the motion from here to here is going to be F dotted with this displacement vector. And that's the point with position vector R, that's position vector R plus dr. So this vector here is just dr. So the work done during this small little excursion is going to be F dot dr. Right. So I'm going to call that dw because, well, I'm using w for work. So this is a differential amount of work done in doing this little thing here, right? So this d here is meant to go with the d on this side as well, right? So this is a differential element. So this also has to be a differential element. So that's the work done in going from here to another point. Well, how do I calculate the work done all the way from the beginning of the curve to the end of the curve? Well, imagine I've broken it up into tiny segments, and I just add each of these together. So I just have to add together all these amounts of work, and a way of thinking about that is over here, right? So I just add together all the work. So adding together all the work done in all these tiny little segments. Over here, a small amount of work done, then a small amount, you add them together. So this corresponds to doing an integral. So this integral here is integration over the curve C. And this is like saying, look, if you, so the intuition is that you do dw and you just get w, right? So that's sort of the intuition. So the total work done is given by doing that integration. And what is dw? Well, dw is this thing over here. So it's F dot dr. Right now, remember that F is varying depending where we are on space, so that's itself a function of the location R as well. So so here's what we have now. So here's a type of integral, and we're going to call this a line integral. You might also call this a path integral, but generally this C here is just any old curve which is in space, right? So you got this sort of integral, and there's a dot product there. That's a vector field. So it's a more complicated type of integral than the type of multiple integrals that we were talking about before. Okay, just a little bit of notation. If we have a closed path, right, a path which comes around and connects back to itself, if it's closed, then the notation that we use is we put a little circle around the integral sign just to indicate that it's closed. Okay, so that's going to be an important notation that we're going to be using as we proceed. All right. Okay, so now the question is, okay, somebody gives us this and someone gives us a curve. Well, how can gives us a curve? So how can we compute such a line integral? Well, let's remind ourselves what this means, right? If I have a vector field like this, the vector field has components. Imagine I'm in R3. So my vector field F, well, it's got one component over here in the I direction, and let me call that F1, which also, of course, depends on location. And then I have F2 in the J direction, in the Y direction, and I have F3 in the Z direction, right? So here is a general form of a vector field in R3. It's going to take that form, right? And a general R, a general location R is going to be given like that, but this is going to be a location on the curve C when you're going to be doing this. So okay, you might remember that what we're looking for is this thing here, right? So F dot dr is what we're looking for. So here's my F. So I have my F. That's R. That's not dr. I need to figure out what dr is, right? So what's my dr going to be? So well, dr is a small line segment that you go along this. It's a small line segment. The line segment is going to have a component in the X direction, Y direction, and Z direction. So basically, I can just write this down as being dx in the I direction plus dy in the J direction plus dz in the K direction. So this is how my dr is general dr is going to look. right? And these correspond to the infinitesimal displacements in each of the x, y, and z directions. And now what I need to do is I need to take the dot product between these two in order to figure this out. So f dot dr, the dot product between these two is, well, it's that times that. So it's f1 times dx plus f2 times dy plus f3 times dz. So I can write it as f1 dx plus f2 dy plus f3 dz. Okay, now this is beginning to look a little bit better because I can kind of understand this more as an integral than this one here, because I've got a nice dx here, right? So because of integration, because of properties of integrals, I can split this into three integrals. So that dx plus that dy plus that dz, right? So I can actually do that. So let's just focus on this integral for now, right? Suppose I was trying to do this. Now, you know, I'm tempted to treat y and z as constants and just simply find the antiderivative of this, because that's the sort of thing that we did in multiple integrals. Because I'm trying to integrate with respect to x, that there's an x over there, and I want to try to think of y and z as constants. But the situation is different here, right? So x, y, z is a general location on my curve. So as I go to different locations, my all three coordinates are going to actually change. So if I change x by a small amount, well, and I remain on the curve, I'm down here on this curve possibly, my y has changed and my z has changed. So there's something going on here. So this is a function of x, and that's also going to be a function of x when I'm trying to do this integral, if I'm just trying to do this first part of an integral. So here's the integration that I need to do. So I'm actually not allowed to treat y and z as if they were constants and do an antiderivative in the way that we would have done in a sort of a multiple integration sense. So if I'm doing the integration with respect to x, I need to figure out what the limits are with respect to x, and I need to know what these functions are, and that's a mess, right? And then I need to do similar things for these other two integrals as well. So this is kind of ugly. So there's a better way to do this, right? So let's, in general, let's just try to make sure that we understand what's going on by looking at an example here, right? So let's look at this example where f is this vector field. So that would be my f1, that would be my f2, and that would be my f3 according to the notation of the previous slides. And let's try to find f dot dr along a curve C. And what is the curve C? The curve C is shown down here, right? So the curve C is a sum of three different curves. So the first curve is a straight line. I go from the origin to the point 1, 0, 0. And the next one is a straight line. I go to the point 1, 1, 0, where y is equal to 1. And then I take a straight line upwards. I go to where z is equal to 1. So I respectively increase x from 0 to 1, then y from 0 to 1, then z from 0 to 1. So here's my curve, right? So let's try to figure out whether we can do this. Well, let's see. Let's look at each of these curves in turn. So on C1, so C1 is this curve. So on C1, what do I know? Along that curve, I know that y is always equal to 0 because my y-axis is pointing in this direction. At every single point, y is equal to 0. Well, z is also equal to 0, right? Because my z-axis is upwards. So these two things are not changing in this case. So even though I was worried about this sort of thing here, so here's a situation in which they're not changing, and the reason why they're not changing is, well, we're going on a straight line in the x direction, purely in the x direction. So these two things are not changing, but x on the other hand is changing from 0 to 1, right? So that's actually changing. Okay, now what I want to do is I want to do this sort of calculation over here. I want to look at this integral here. All of these things here. So in order to do that, not only do I need to know x, y, and z values, I need to have some understanding of the dx, dy, and dz. Now, in this case, I can actually say that dy is equal to 0, right? Because it's an interpretation, right? So dy is the change in y. At every single point as I'm going along, this y is not changing. So dy is identically equal to 0 as is dz. So dz equals 0 as well. Okay, so this tells me that when I'm doing this integral along C1, when I'm doing the integral, when I take f dot dr, so of the three terms, I'm supposed to have these three terms here, right? So f1 dx plus f2 dy plus f3 dz, I'm supposed to have those three terms, but dy is equal to 0 and dz is equal to 0. So I'm only left with the first term. So I just have f1 of x, y, z and dx. That's all I'm left with. Yeah, because dx is the only one of the differential elements which is non-zero. Okay, so I have that, and what else do I have? I have the fact that x varies from 0 to 1. I'm going along the x-axis. X is 0 there and x is 1 there. So x varies from 0 to 1. So I can put in the limit 0 to 1 here. Okay, can I do this integral? Well, what is my f1 in this case? My f1 is that. So, oh, that's easy. So that's just the function x squared. So I have 0 to 1 of x squared dx, and this is easy to do. It's x cubed over 3, 0 to 1. So that's 1/3. Yeah. So I'm going to get 1/3 over here. Okay. Just point out something a little more than that. When I write down f1 of x, y, and z, this is actually incorrect, because I need to write down the values here which are along my curve C1. So along my curve C1, yes, x is changing, so that I have to retain the x dependence there. On the other hand, y and z are not changing in this particular case, because as I'm going along this, y is always equal to 0 and x is always equal to 0. So both of these are 0. Yeah. So because I have that, so even if this function actually had y's and z's in it, what I need to do is I need to evaluate that at y equals 0 and z equals 0, because at every single point along my curve of interest, y is equal to 0 and x is equal to 0. And that's going to reduce this to a purely function of x integrated with respect to x. So I can actually do this because I'm going along that straight line, right? So let me very quickly show you what would happen for the next part. So along C2, so as you're going along C2, what do we know? And x is now equal to 1 because I've come to x equals 1. Z is still equal to 0 because I haven't gone upwards, but y changes in this case. So dx is equal to 0 because x is not changing as I'm going along this. X is always equal to 1 at every single point, which means that there's no change in x. There's also no change in y. So when I calculate f dot dr in this case, I don't have f1 dx, I don't have f3 dy, I only have f2 in this case. And once again, we notice that now what I can do here is I can actually figure out what's going on here. Oops, erase the wrong things. So x is always equal to 1 in this case, and z is always equal to 0. On the other hand, y is the one which is changing, right? So that's what I need to do, right? So f2 at x, y, and z. So those are the values. So this is purely a function of y in this case, but well, over here it just has a y squared anyway, so the x and y values were irrelevant, but anyway, so it's just y squared dy, so that's going to be a third as well, right? So similarly for this case, so once again, I'm going to be I'm going to put in the values now. X is equal to 1 and y is equal to 1 in this case. I won't go through this in detail, but it's exactly the same sort of analysis. And I'm going to get a third for C3. And once we figure this out, now what I want is the integral over the entire curve, which is that plus that plus that. So it's going to be 1/3 plus 1/3 plus 1/3, and the answer is 1. Okay, so this was all good. We were able to use this interpretation of f1 dx plus f2 dy plus f3 dz because it turned out that the other variables, the y and the z, for example, when we were doing the x integral, did not change, right? So that's why we were able to do this. Okay, so this can only be applied for curves which can be decomposed into lines parallel to the coordinate axes. Because if you're going parallel to one of the coordinate axes, say the y-axis, if you're going parallel to the y-axis, that means your x is not changing and your z is not changing, right? So that dx is 0 and dz is 0. So you're able to do this. Well, let's take the next step. If we have a general curve C, then how do we do this? Right, so then when you're going from a general location to the next location, all three coordinates in general are changing. So how do we do this? And that's something that we're going to be discussing in the next lecture.